Welcome back to Nature's Waterworks, How Lakes and Rivers Function. This is part 5 of 7, Classification of Water Bodies. I'm Robert Holmberg from Science Outreach, Athabasca. Okay, here's the outline of the whole larger presentation, and we're now on number 5. Classification of water bodies. And many ways of classifying water bodies. You can look at their geological origin, you can look at their number of surface outlets, you can look at their nutrient content, you can look at salt content, you can look at flushing times, and this one and the surface outlets are only relatable to lakes. Now, with glacial, we can have eroded basins, we can have kettle lakes, we can have tarn lakes, rifts or fractures, avalanche caused, volcanic, again only for lakes, and meteorologic, and also only for lakes. So here's the first one, glacial eroded basins. You can see from this photograph, the glaciers have carved long channels moving from the left of this photograph to the right, and cause these depressions. These depressions fill with water and form water bodies. With kettle or pothole lakes, what happens is that big chunks of ice break off from the retreating glacier into the glacial till and form lakes. And the aerial photograph is showing a number of potholes from the prairie region of Canada. And these blocks of life, blocks left will melt and form these water bodies. And they can be quite small, 5 meters, to fairly large, 13 kilometers in diameter. They're often roundish in form, but they don't necessarily have to be. And then you can have tarn lakes, and these are formed in cirques, which are valleys, amphitheater-like valleys created by glaciers, and then these are formed within these cirques. And what happens is the glacier digs out a deeper channel and has a deposition of material at the lower part, and that forms a bit of a barrier, and then keeps water inside of this depression within a valley. And then you can have rifts or faults, and these are elongate, deep, large volume, and old lakes. And we've talked about Baikal, but also in this diagram we show Tanganyika and Malawi in Eastern Africa. And then you can have rock falls or avalanches. And this is an example. In 1959, there was a rock slide into the Madison River in Montana, and it formed Earthquake Lake. And here's the lake. And then you can have volcanic craters, and this is Crater Lake in Oregon. And they tend to also be roundish in their outside their outline. And then you can have meteorites that make an impact crater, and this is one in northern Quebec. And the material in the center blew up, and you've got this round circular lake. Okay, we can also look at the number of outlet streams, and we have to distinguish between outlets and outputs. All lakes have got 3 well, not all lakes, but they have up to 3 outputs. They consist of outlet streams, and there's evaporation, which is water only, of course, and then there's groundwater. So you can have closed and open lakes. And so near Baptiste Lake, which I've talked about before, there's lake number 1 and lake number 2. And these are their official titles because nobody had a name for them when they were surveyed. And this is close to home, and that circle shows where I live. So lake number 1 is a closed drainage basin lake, and that has 0 outlet streams, but occasionally it can overflow. And probably at one time, lake number 1 had a stream that flowed into lake number 2, but it's now been vegetated over and there's probably groundwater connection, but it's only limited to two outputs, evaporation and groundwater. Now, this leads to retention of particulate and dissolved substances, and so they become more nutrient rich. But also, because they have no outlet, they're very susceptible to highly fluctuating water levels from variation in precipitation. So you can get temporal changes in their sizes and their shapes, whether you get high or low amounts of precipitation. Okay, now we'll move on to lake number 2. This is an example of an open drainage lake, and it's got one kind of outlet. In this particular case, we'll talk about the 2 in a moment. So it's got the 3 outputs. It's got the outlet stream, and it's got evaporation and groundwater. So there's less retention of particulate and dissolved materials. So once in a while, you have open drainage lakes that have 2 outlet streams, bifurcation lakes they're called, and they're usually found in the upper regions of basins, and they lead into 2 drainage basins. An example is Wollaston Lake in the province of Saskatchewan, which has the Fond du Lac River, which flows into the Arctic Ocean, and the Cochrane River, which flows into Hudson Bay. But these are, as I say, very rare type of lakes. Now, we can also classify water bodies by the nutrients that they contain. But before we talk about that, we've got to give some background information. So the inputs to water bodies comes from precipitation, which is basically water, but then there's runoff from the land, there's inputs from various tributaries, groundwater can contribute to it as well. And these inputs and outputs of water bodies, of course, there's water, but there's particulate matter or suspended materials. And then there's dissolved chemicals, and these are often ions. Now, nutrients for photosynthesis, or which regulates productivity of lakes and rivers, is mostly on three kinds of chemicals: phosphorus, like phosphate ions; potassium, like potassium ions; and nitrogen, such as nitrites, nitrates, ammonia, and things like that. All 3 of these are usually considered as typical fertilizers, and so regulate photosynthesis. So the sources of nutrient inputs to water is, say, from the atmosphere. You can get dust, you can get sewage runoff, you can get diffuse runoff from fields and areas, and there's groundwater. So vegetation removal leads to erosion, leads to nutrient input. And this is an aerial photograph of a nearby lake where people are trying to remove the vegetation to get a beach area. And you can see that by clearing the vegetation, nutrients are flowing into the lake from the shore. So you can classify water bodies with their nutrients into 4 different groups, and there's oligotrophic, which have few nutrients, and they tend to be young lakes. They tend to be in the headwaters. They tend to be cold. They can tend to be deep, and they have less than 0.1 grams per kilogram of phosphorus. So then you have mesotropic, which have a little bit more of nutrients, say 0.1 to 0.3 grams per kilogram of phosphorus. And then you have eutrophic, which have lots of nutrients, 0.3 to 1 gram per kilogram of phosphorus. And then you have hypertrophic lakes, which are very high levels of nutrients. These tend to be old, downstream, warm, shallow lakes, and they'll have more than 1 gram per kilogram of phosphorus. So all of this increase in nutrients it leads to what we call eutrophication. And eutrophication means that you often get blooms or high populations of algae and cyanobacteria. And this is an example from the Yellow Sea in China. Not a nice place to swim. Now, all lakes have a lifespan. They gradually fill up with sediment and cease to become lakes. They may be wetlands for a while and then they become dry land. So what happens is that with eutrophication, the lifespan of lakes, rather than being centuries, maybe go down to decades because they fill in faster. Now we can also, excuse me, classify water bodies by their salt content. And salts are ionic compounds of cations such as sodium and calcium, and anions such as chlorine, carbonate, and sulfate. So fresh water is defined as less than 0.5 grams per kilogram, and that's not a percentage, that's a parts per thousand sign. So that's fresh water. Brackish water, which you wouldn't want to drink if you could help it, it'd be 0.5 to 30 grams per kilogram. Saline water is 30 to 50 grams per kilogram. And briny water is more than 50 grams per kilogram. And to give you a comparison, oceans are only 34 to 36 grams per kilogram. So they're saline, they're not briny. And within the salt lakes, you can talk about alkaline or sodium soda lakes because they have got a lot of carbonate ions in them. And they have a higher pH, 9 to 12. So an example is this Lake Van in Turkey with a pH 9.7 and 9.8, varies with the amount of precipitation, and the salinity is 23 grams per kilogram, so they're brackish. And here's another example of a saline lake, the Great Salt Lake of Utah, and it's briny. And you can see that it's sort of divided basically in half because there's a railroad track that goes across it and closes off a lot of the communication of water between the north and the south. And the salinity difference affects organism growth. So the one towards the north is brownish because of whatever algae or cyanobacteria are living in there, and the bottom one is greenish. And the greenish one is got 142 grams per kilogram, and the northern one is far more salty. On the Aral Sea is a saline lake, especially now. It used to be the third to fourth largest lake in the world. So there's a satellite image of 1989 and then another one of 2014. And what has happened here is that in the 1960s, several rivers that flowed into the Aral Sea were diverted for agricultural use, especially for cotton growth, and decreased the volume of the lake considerably, and it became more saline. This is being reversed a bit today by stopping some of the diversion. Yes, increased salinity. But the Aral Sea used to have a major fishery, and you can see from this boat, it's collapsed. Here's an example of Lake Vanda from Antarctica. It's a saline lake. It's a closed water body, third most saline water body in the world. Salinity is over 350 grams per kilogram, so it's definitely briny. And in the summertime, it melts along the edges. Just for added information, it's fed by the longest river in the Antarctic, the Onyx, but it's a very short river. Here's another saline lake or pond, Don Juan Pond in Antarctica. It's at the end of a rock glacier. That's a glacier with lots of rock in it as well as ice. And it's, again, a closed water body, second to sixth most saline water body in the world. and it varies between 200 and 474 grams per kilogram, mostly of calcium chloride and sodium chloride. And because of a high concentration of salt, it does not tend to freeze. Now, the fifth way of classifying lakes, not rivers, is by the flushing or residence times. And this is the time to replace, theoretically, all the water in a lake. And that varies a great deal with lake volume, with the size and form of the drainage basin, and the amount of precipitation in the area, and the amount of flow by streams and groundwater that goes into these lakes. And flushing time removes nutrients and so affects nutrient residence times as well. And I've put in a diagram of a toilet because flushing is a way of remembering it. So these are lakes from Alberta. They vary in their flushing time. So the Baptiste Lake has got less than 10 years of a flushing time, while Pigeon Lake on the right is more of a century. So lakes in various areas vary with their flushing time. And that is the end of this part. We will then go on to the next one.